Hello, you've joined Restless Seas, a Woods Hole Oceanographic Institution Ocean Encounters presentation about ocean currents. We have a lot of people joining us tonight, so please bear with us. We'll get started very shortly. And now, please take a moment to read WHOI's land acknowledgement.
The ocean covers 70% of the globe. It gives us oxygen and food and millions of jobs. It brings joy and shapes our climate and weather. The ocean is life, and it belongs to everyone. Woods Hole Oceanographic Institution is the world's independent leader in ocean discovery, exploration, and education, working to understand and sustain one of humanity's most precious common resources. Join us today for our ocean, our planet, and our future.
Welcome to Ocean Encounters, a virtual series from Woods Hole Oceanographic Institution, or WHOI as we like to call it for short. Tonight's event is Restless Seas, How Ocean Currents Shape Weather, Climate, and Life. My name is Veronique LaCapra. I'm the host of Ocean Encounters, which is now in its 6th season. WHOI's Ocean Encounters event series is an endorsed activity of the UN Decade of Ocean Science for Sustainable Development. Ocean Encounters is also made possible in part by our sponsors, the Avatar Alliance Foundation and Dalio Philanthropies. So thank you to them. Thank you also to any WHOI members who are joining us tonight. You are the heroes at the heart of our efforts. I hope also that everyone in the Northern Hemisphere had a great summer. It's really great to be back with all of you. Before I introduce our speakers, I want to let our Zoom audience know how they can participate in tonight's live Q&A. If you have a question for one of our panelists, please use the Q&A button on your Zoom screen and type your question in the little window that appears. You might be more used to using the chat function in Zoom, but tonight, please use the Q&A button instead. We often get hundreds of questions, so I apologize if we don't get to yours while we're live. You can ask questions anytime, starting now. I also want to let you know that we are recording this event. That video recording will be made available on the whoi.edu website. We had more than 3,200 people pre-register to join us tonight on Zoom, which is a record for us here at Ocean Encounters. We also have viewers joining us right now on Facebook and on YouTube. Thank you and welcome to everybody. Let's get started. Even on the calmest day, the ocean is constantly in motion. From powerful ocean currents to the smallest eddy, moving seawater is a key driver of the Earth system, distributing heat, nutrients, and carbon. This motion sustains life at every scale and shapes weather and climate around the globe. Tonight, we'll talk about ocean currents, how they're changing, and the implications for marine life and for all of us. Joining us are three WHOI physical oceanographers. They are Amala Mahadevan, Svenja Ryan, and Gordon Zhang. Welcome, everybody. I'd like to start with explaining some terms that might be unfamiliar to some of our viewers. Amala, I think I know, but what exactly is an ocean current? How would you define it?
Yeah, so you can think of an ocean current literally as a river in the sea, where the water is moving at a faster speed and in a preferred direction as compared to the surrounding water. And these concentrated flows can be very large. You can also have small currents. They're typically faster near the surface. Roughly 1 to 2 meters per second is a very fast current, which is like a slow cyclist, but actually transports a lot of water. So the Gulf Stream, for example, is a major current, and it transports about 150 Amazon rivers. That's how much it transports per second, So that's considered like 30 square drips, 30 million cubic meters per second is the transport of the Gulf Stream is estimated to be. And what you're seeing in this animation here is the currents around the world, and the white is displaying the speed of the currents. The more white, the faster the currents are moving. And you can see that the flow is concentrated in certain currents. The currents are meandering. They're forming these little loops or meanders, and some of these loops are breaking off to form what we call eddies. And what you see right now in the frame is the Kuroshio going up the coast across from Japan. You see the Gules current, and coming down the coast of Africa, you see the Antarctic circumpolar current, and earlier you saw the Gulf Stream. So they're all over the globe and transporting things around.
Are currents only in the surface ocean? You talked about how they're stronger at the surface, but are there some currents that are actually like at the bottom of the ocean?
Yes, so we have deep currents like the deep western boundary currents. They're not as strong and they're not as concentrated. And actually, they are quite difficult to discover because at the surface, we can see them. And I'll talk about the ways in which you can see them at the surface. But deep down in the ocean, how do we measure them? We really have to get our instruments down there to measure them. And they're also
right. So let's talk more about that. How do we measure currents in the ocean? And maybe give us a little bit of a history about that.
Yeah, sure. So some time ago, when sailors, used to cross the oceans, they were aware of currents because their vessels got pushed around, and they would throw into the oceans like a corked bottle, and they could find later the bottle would show up on some shore, and depending on when and where it showed up, they could tell that the current carried it there, and they could roughly estimate the direction of the current depending where they threw it and where it came up, where it landed. And they could also tell how long it took, so roughly the speed. But these days, what we use is something called drifters, which are essentially buoys that we drop in the ocean. And these buoys have GPS and they have a drogue. And what you're seeing here in this video is one of our research expeditions in the Western Mediterranean Sea. The blue dot is the ship, and it's zipping around, and it's, of course, speeded up. This is over the course of about 10 days. So we took a ship, and we went around with the ship, and we were dropping these drifters in the oceans. The drifters have GPS, so they're relaying their position back to satellite, and you can see the tail of the drifter where it's been. So over the course of this little ship excursion, we were able to trace out what the flow is by dropping these drifters in the oceans. And this is the western part of the Mediterranean. To the extreme left is the Straits of Gibraltar, Spain to the north, and Morocco to the south. And you can see these big looping features that are made by the currents, the gyres that are.
Yeah, it's fascinating.
So another way that you can measure currents these days is using satellite. And satellites are able to measure the sea surface topography. So that's the sea elevation that they can measure very accurately. And this is on large scale. So we're not talking about waves, surface waves, but the sea surface is raised. And where it's raised, you can imagine the pressure is higher compared to where the sea surface is lower. So the surface pressure of the ocean is what you're measuring when you measure the sea level or the sea surface topography. And you'll see that the ocean surface is not flat at large scales. Some places are elevated compared to the others. Those places have higher pressure, and the currents can be estimated from the surface pressure field, and they're proportional to the slope of that topography. So the more steeply sloping the topography, the faster the current, and they're going to follow the contours of that topography. So we get a good picture from satellite these days on large scales.
Well, thank you, Amala. Svenja, what kind of tools do you use in your work on currents?
Yeah, well, I use quite a few different tools. Traditionally, we can go out to sea and measure currents there, but I'm really excited about, as Kamala explained, the sea surface height measurements, because just last year, NASA, in collaboration with the French Space Agency, they launched this new satellite, which really gives us new high precision data of sea level, sea surface height. And so, as you can see in this image, in the past, there were missions. They started in the 1990s. And throughout the time, we were able to measure the sea surface more accurately. And since last year, as you can see here now, we really can get down to very, very small scales. And the first images that we've seen and the community has seen really indicates that these measurements will kind of revolutionize the way we do oceanography, because we can get down to these small scales. They can tell us about new physical processes. And yeah, here you can see an image with an example in the background. The kind of fainter colors are the traditional measurements that we had in the past decades, and you need multiple satellites blended together to create such a map. And now with this new measurement, you can see this brighter, what we call swath band in the middle. This is the new measurements that we can get. So you can get really to these.
Well, that's incredible. It's much, much more defined now.
Yeah, exactly. So now we can get down to scales of like 6 to 9 miles, whereas before we were down at 18 miles or something like that. And we get this 2D view along this band. So we're very excited about that.
All right, thanks, Svenja. Gordon, in my introduction tonight, I said that you and the other speakers were physical oceanographers. Do physical oceanographers just study major currents like the Gulf Stream and those other currents that Amala mentioned earlier? Or what other ways does water move, and what kind of tools or approaches do you use to study those?
Sure, yeah. So besides those major currents, a lot of them we're familiar with, but there are also other phenomena, physical phenomena in the ocean that we study, like eddies that Amala mentioned, and also tides that we all experience every day on the shore, and also we call internal waves, and also upwelling flow, and also small scale flows over coral reefs, say. And so like the eddies Amala mentioned earlier, as you can see from this image, so you have the Gulf Stream, which is a relatively straight or long white lines on the east coast of the United States. But then off that, you can see all these loops. Those are the basic vortexes formed in the ocean.
Little circular areas are.
Yeah. So and also in the Gulf of Mexico to the west of Florida, you see there are loops there as well. Those vortexes, just like the vortexes in the rivers. If you go to the bank of river, you'll see sometimes there are vortexes there too. So there's similar thing in the ocean, but it's much larger scale. So those are the big vortexes or big eddies, but there are also small eddies. If you look closely, like the Mississippi outflow, there's small eddies there as well. So those are eddies we study. And also, like I mentioned earlier, there are internal waves. So we all know the waves on the surface we see every day if we go onto the beach, but then below the surface, there are also waves. Those waves actually are much larger in terms of the amplitude. So this is an image I took from the ocean to the west of Thailand. So I went there. I just used an acoustic instrument. Basically, it's a fish finder, similar to the fish finder we use, and mount it on the bottom of the boat and look down. So in this case, what we are seeing is the tiny zooplankton, the tiny animals, and also fish. in the water column. And you can see the yellow or the greenish color move up and down. The horizontal is time. The vertical is the depth. The total water depth is about 250 feet. But then you see that yellowish or greenish going up and down over maybe 100 feet. So that is actually the zooplankton or fish being moving up and down in the water column by 100 feet. It's like half of the water column. So to them, it's basically they're taking a roller coaster, going really up and then really going down over a course of maybe half an hour. So it's a slower roller coaster, but it's still a very steep roller coaster. So that's the internal waves. There are plenty of them in the ocean that are hidden from us. We don't really see them every day, but they're there. They affect biology, they affect chemistry, they affect sediment transport in the ocean. So, and then there are also other phenomena in the ocean, like upwelling flow. So besides the horizontal flow we see from the satellite, beautiful satellite images, there are also flow going vertical, sometimes going upward, sometimes going downward. The upward flow could bring up the deep water, which has a lot of nutrients in it, and then bring to the surface lit area where the plankton can grow. So that's affect biology as well.
And we'll talk more about that later on in tonight's program. Amala, why is ocean water always moving? What are some of the forces that are driving all this motion?
So the primary driver of the oceans is the atmosphere or the winds. And the winds are always blowing over the earth. This is an image of the winds. I think we took this from yesterday. This is what the winds look like over the Atlantic. And you can see that when the winds blow over water, they are going to apply a stress on the sea surface and move the water with the winds. So they are imparting momentum, or they're doing work on the ocean surface and start to get the water moving. The winds can also create differences in pressure by piling up the water somewhere and creating a higher elevation than somewhere else.
So is that where you get that topography you were talking about before?
So it's partly winds, but the other factor is going to be density. So the water's density is affected by temperature and salinity. And warmer water is lighter or less dense than colder water. Similarly, saltier water or more saline water is going to be more dense than fresher water. What we're looking at here is an image of sea surface temperature. And what you see, so this is the Horn of Africa, the southern tip of Africa, sorry. And you can see that red is warmer water and blue is colder water. So where the water is warm, it expands, it's compared to the colder water, and it occupies a greater height of the sea surface. So differences in density combined with the wind moving the water around create ocean differences in surface pressure. And now if you look at the surface topography of the ocean, so this is what the topography looks like, it's elevated in some places and depressed in other places. So it's creating differences in pressure. And if you were to create differences in pressure in a swimming pool, you'd think that the water goes downhill, or if you tilt a plate, tilt a channel with water, it'll go downhill. But there's another factor that affects this flow in the oceans, and that's the Coriolis effect. The Coriolis effect is because we are on a rotating Earth, and we're observing everything on a rotating Earth. So think of yourself on a merry-go-round, and you try to pass the ball to someone across you. And even if you throw it straight, because the merry-go-round is turning, let's say it's turning clockwise, looking at the Earth from above in the North Pole, then the ball would swing in the same clockwise motion, and we wouldn't be able to throw it straight to the person ahead of you. So it's not a real force, but because we are on the rotating Earth, everything takes this curved trajectory, and in the northern hemisphere, it'll deflect in the same direction. As in both cases, the direction of the rotations will be to the right in the northern hemisphere. If I look at the Earth from the southern pole, then you'll find that the Earth is rotating anti-clockwise if I'm staring at it from the southern pole, so everything deflects to its left. And as a result of this, what happens is when you have differences in pressure, the water is not going to flow downhill, but it's going to flow along the lines of constant topography. So now think of a topographic map, which is the pressure field or sea level of the ocean surface. And the water is going to follow the lines of topography or the contour lines of that map in the northern hemisphere, keeping the higher elevation on the right, and in the southern hemisphere, the higher elevation on the left. And so that's an explanation for how you can deduce these currents by looking at the sea surface topography. That's a good approximation of the currents. There's a little bit more than that too.
Yeah, so interesting. Ken Costell is behind the scenes, my colleague, fielding audience questions, and I'd like to bring in the audience to our conversation now. Ken, do we have any early questions this evening?
We do. As you can imagine, a lot of the questions are about warming and effects on currents, which I know you're going to be getting to in the next section. But Nafiz asks, how are you able to differentiate measurements of surface currents versus deep water currents?
Yeah, so do you want me to take that, or I'm
Yeah,
sorry.
go ahead, Amala.
Yeah, so surface currents, I think you can tell by drifting objects at the surface as I measure, or measurements at the surface, or looking at sea surface pressure or sea elevation at the surface. Deeper currents, you really need to measure deeper in the ocean what's happening. We can figure out from models, so differences in density cause deeper currents. You could have a current going in the opposite direction at depth. So you, for example, have an equatorial current and you have an equatorial undercurrent. You have a western boundary, a deep western boundary current. And some of these currents, so they depend on what the density gradients are. And to measure them, we need to measure at least the temperature and salinity. So from density, we can figure out what the pressure field is and figure out the flow. Or we need to make measurements of the flow itself, and we use acoustic methods there to figure out what the speed of the water is by looking at the scattering from particles, the rebound of a sound wave from particles that are being carried with the flow.
Can I add a little bit to that?
Yes.
For sure.
Yeah, so there are also, so Amala earlier showed the drifters you can throw to the ocean surface, and then from the GPS, you know exactly when they are, where they are, right? But there are also drifters people can put into the deep ocean, and they pre-program the drifter, so they are staying at a particular density, a particular water depth, basically, and they just go with the deep current, and then for a period of time, say a month or a week, and then once the time reaches, and then they will flow up to the surface, so you know how far within that period at the deep ocean that drifter has moved. And there are also other measurement. Instead of you have to wait till the surface, there are also, as Amala mentioned, we use acoustics, so sound. So we don't have GPS underwater, but we can, there's sound propagated underwater pretty efficiently. So you actually have, we call a hydrophone in the drifters, and so you have moorings in the ocean. You can emit sound, and those drifters, the hydrophone in the drifters, as they move, they will hear the sound. And then if you have multiple sources in the different places of the ocean, you hear those different sound at different time. From those tiny difference in the time, you can figure out where exactly the drifters are, even underneath the surface. So it's basically like GPS, but it's underwater, but using acoustics. So from there, you also can measure the deep flow in the ocean.
Yeah, and we call those drifters that are under the water floats. There's a very funny door sign at WHOI that someone has, which says that drifters float and floats sink. That's just terminology that oceanographers use for floats at the surface, drifters at the surface. Yeah.
All right, we've heard about the different ways that ocean water moves and how we can measure those movements. Now I want to get into why an ocean in motion matters. In other words, what role the movement of the ocean water plays in ocean ecosystems and more broadly. Svenja, let's start with a major ocean current that we've been talking about, the Gulf Stream. Where is it and what does it affect?
Yeah, so as mentioned before, the Gulf Stream is one of the strongest currents that we have in the ocean, and it flows northward along the western boundary of the Atlantic Ocean. So you can see it here by those bright colors that move northward east of Florida. And the Gulf Stream separates roughly at Cape Hatteras, so in the middle of this picture, where these warm colors move away from the coast. And as Amala said earlier already, these currents, they transport stuff around, including heat. So it's huge amounts of volume that they transport. The Gulf Stream has 30 Swerdrup, as Amala said, or 30 million cubic meters. And to give another number as reference, that equals the volume of 12,000 Olympic swimming pools. So it's huge water masses that move along per second. And especially the Gulf Stream moves a lot of heat northward. Once it separates from the coast, we kind of rename it a little bit into North Atlantic Current. But this North Atlantic Current really flows across the Atlantic Ocean and carries this heat towards, for example, Europe and higher latitudes. And it's one of the reasons why Europe actually has a milder and more temperate climate, because of this heat that's being carried northward, and that heat gets released to the atmosphere as the atmosphere gets colder in the north, and really can warm the regions there. It also plays an important role in our global circulation. So it's not just there to warm Europe. I'm from Europe, so I enjoy the warmth there, obviously, but it really plays a big role in our global overturning circulation, what we call it. So it carries this heat northward, as you can see here on the schematic, and it loses the heat in those polar, subpolar regions. And because the water is salty, as we heard from Amala, salt makes the water dense. And if we additionally cool it, it becomes even denser. So it can really sink to great depth, to 2,000, 3,000 meters in those regions, and feed kind of a deeper branch of our global ocean circulation, where it then returns southward, as we can see here by these bluish wide arrows.
All right, and just to name this whole big circulation system is sometimes called the AMOC. I can never remember what that stands for exactly.
It's right. It stands for the Atlantic Meridional Overturning Circulation, and this overturning implies that you carry something northward in the upper part of the ocean, which the Gulf Stream is part of it, and then this water becomes denser, sinks, and you return the flow at great depth. So it's like this overturning from shallow to deeper waters.
Okay. So we heard that the Gulf Stream warms Europe. That's important. But in preparing for tonight, I learned that one of the most powerful currents in the world is actually around Antarctica. It's called the Antarctic Circumpolar Current. Tell us about that and why it's different from, say, a current like the Gulf Stream.
Yeah, so currents like the Gulf Stream are really affected by the continents. So the continental boundary the continents found the boundaries of this ocean basin, and the current hugs the boundary for a while and then veers off. The Antarctic Circumpolar Current is one of the only major currents that flows unobstructed across the whole Earth, like circumnavigates the whole Earth. And it follows the same direction as the wind. If you're looking down on Antarctica, it's going clockwise in this case, and it's transporting a lot of water. And it's actually, the winds are really roaring in this region. Is one of the stormiest parts of the ocean. And so this current is a really powerful current. But you can also think of a current as a barrier to transport across the current. And I say that because currents are also fronts. A front is a barrier in density. So in the case of this Antarctic Circumpolar Current, you have denser water closer to Antarctica, cold, dense, salty water closer to Antarctica. And off or towards the equator, you have lighter water or warmer water. And the current acts as a barrier. It transports mostly in the direction of the current, but it's preventing transport across the current because those are different density waters that don't mix very easily. That's really important for our climate of the Earth because it's what isolates or insulates Antarctica and allows the ice sheet on Antarctica to be maintained. If heat were transported from the tropics and subtropics all the way, like some of the other regions of the Earth, they would reach the Antarctic continent and melt the ice. So the ACC, or the Antarctic Circumpolar Current, is a barrier as much as it is a current. It's a barrier to heat.
Interesting. So Svenja, before joining us as a scientist here at WHOI, I know you did your PhD research in Antarctica. What were you studying there and what did you find out?
Yes. So as Amala said, the ACC, the Antarctic Circumpolar Current, is mostly a barrier to the heat, from the heat that prevents the heat from moving towards Antarctica. But there are regions, as you can see in this image, where the current moves closer to the coast. So for example, on the western side of the Antarctic Peninsula, or also in other regions, we have some transport of this heat that's moving towards the continent. Eddies, for example, are an important process to transfer this heat. And so my research was really about a particular region in Antarctica where I tried to get a better idea of how much of this heat and how frequently can really reach one of the largest ice shelves in the region. And so yeah, these are just a couple of snapshots from me in field work. In this one, we took a ride. Usually we go out on the icebreaker on a research vessel, but we were allowed to visit the German research station there. So it was like an hour-long bumpy ride on this sled in very, very cold conditions, as you might imagine.
It looks cold.
It was cold, but it's part of the experience. And yeah, just turn the light off. Yeah, and this is just me on one of these ice shelves. So we were actually allowed to go on land because we had to drop off some supplies. And yeah, so
that's the icebreaker behind you, the ship.
Right, that's the German ship, the Polarstern. And so an important fact to mention is that the heat that comes to the Antarctic ice sheet really comes from the ocean, and it's found at mid-depth. In contrast to the Greenland ice sheet, where a lot of melting really happens from the warm atmosphere at the surface, because Antarctica is so shielded, still that heat comes from the ocean at mid-depth. And I should mention heat means the waters can be like 0 degrees Celsius or 32 degrees Fahrenheit.
But
so
it's the difference
kind
between
of cold, but
yeah.
for ice, it's still warm. It can still melt ice. And so as you can see in the schematic, this red blob here kind of indicates this warm mid-depth water. And we have these floating extensions of the Antarctic ice sheet, which we call ice shelf. And the the water is able to penetrate below this floating ice tongue, and we call these cavities. And this gray line kind of indicates, again, a front, as Amala said, so it separates this warm water at depth from this colder water that's sitting above it. But certain processes happen that allow this warm water to move into the cavity. And once this warm water actually reaches the ice shelf base, it can start melting, as you can see here on the left. And this melting process then modifies our water properties. It introduces meltwater into the water column and makes this water lighter. So again, we have also within this cavity kind of an overturning circulation.
Because that melting water or that meltwater is fresher, right? Is that, yeah.
And in these cold temperatures, it's really the salinity, so the amount of salt that we have in the ocean that controls the density. So when we introduce fresh water, that really makes it lighter, and everything's cold anyway.
Yeah, so has this melting always happened? If we could go back to that previous image just for 1 second, I'm just wondering, has this process always been going on, or is climate change playing a role in this as well? Svenja?
Yeah, I mean, that's what we're studying. There are indications that some of it has always happened. It's part of the natural cycle, same as we lose icebergs. They carve off very frequently, but there are indications that in the recent decades, we have in certain hotspots where more of this warm water really gets onto the ice shelf, and a huge amount of the ice is melting from underneath. Yeah.
So, Veronica, can I add something here? This is
Absolutely.
very interesting
Go
topic.
ahead.
Yeah, so one thing, earlier the global view of Antarctica, I feel like that's very far away from where we live, right? But it's actually, so even though the process Svenja just described, they are indeed very far away from our everyday life, but they're actually not. They can direct affect our lives, and there's different ways that could affect us, but one way that could potentially can affect us is through the sea level rise. And so here I want to introduce maybe different type of ice. Now in the around Antarctica, we have the sea ice that are formed from frozen from the seawater that you can see from on this particular diagram on the right, that's a floating, very relatively thin sea ice. Then in the middle is the ice shelf that Svenja just described. Those are actually hundreds of meters, maybe a couple of thousand feet deep, floating in the ocean. They're thick. Now on this diagram, it looks very thin, but they're really thick underneath this ocean. but this ice shelf actually came from the glacier ice on the continent, right? So on the continent, we have miles and miles of ice. But when I talk about miles and miles, I'm not talking about the horizontal direction. I'm talking about the vertical direction.
Depth,
So
yeah.
above us, miles and miles of ice sitting on the continent, and they are gradually moving towards the ocean. And then once they reach the ocean, and they float on the surface, and so that's the ice shelf. So Svenja just said how describe how the ocean could melt the ice shelf from below. So ice shelf, they are already floating. They actually already, and their melting does not contribute to sea level rise because they're already floating. But then the glacial ice behind them, when they melt, they will, right? So the ice shelves, they are just like the corks in a wine bottle. They are protecting the glacier from going into the ocean. They are slowing the glacier down, right? So when the ice shelf melts, break off, and then the glacier will move faster into the ocean. That part will cause the sea level to rise, and not only locally, but also globally. So that will affect, even though it's far away, but it will affect our everyday life through this sea level rise.
Yeah, and just to add this, so I think in this coming century, this melting from the Antarctic ice sheet is really expected to be the major contributor to global sea level rise, because there are these huge volumes that are currently still sitting on land, but they can potentially feed or flow, because the ice is a liquid in the end, flow into the ocean and be melted.
Yeah, so I think it's that distinction you made between these different kinds of ice. I found that really interesting. So even something massive like the ice shelf, because it's already floating on the water, it's not going to contribute to sea level rise, even if the whole thing melts. But if the whole thing melts, like you said, the glacier is then going to move faster, and that will change things. And probably pretty catastrophically, I would think. Like it could happen quite quickly once that cork is out of the bottle.
Yeah, it is. So one of the places called Sweet Ice Shelf on the western side of the Antarctica. The ice shelf is melting fast, and the glacier is really moving fast towards the ocean.
And I think just to give you a number, so if the whole Antarctic ice sheet, which most likely will not happen in the near future, but if all of that melted, it would be an equivalent of roughly 57 meters sea level rise. So it's a huge amount of volume.
Wow. Yeah.
Come out.
All right. I bet we have a lot of audience questions at this point. Ken, what do you have for us?
Well, we have over 30 questions so far, and quite a few of them are asking about some version of our currents slowing as a result of warming. Is the AMOC slowing? Is the Gulf Stream slowing? One person even asks, he had heard that there was a possibility that the Gulf Stream could reverse, which I don't think if it's on a rotating sphere in the northern hemisphere. But anyway. Well,
I could say something to that.
Sure, go ahead, Svenja.
Yeah, and certainly I think it's been a lot in the news. So the Gulf Stream is slowing, the AMOC is shutting down. It's often not quite clear what the difference between the AMOC and the Gulf Stream is. So as I said earlier, the Gulf Stream is part of the AMOC of this overturning circulation, because it is an important transport mechanism and transport heat northward. But the AMOC itself really is kind of a construct that helps us describing this overturning circulation, which in itself is driven by many different processes. So for example, the Gulf Stream in itself is mostly a wind-driven current that is not directly the AMOC. And there's certainly indications in past climate, so climate reconstructions, that there were climate stages where the AMOC, this overturning circulation, was slower. That just means that you don't form quite as dense water masses in the north, so they don't sink quite as deep. And this whole process is slowing down. And with that, there might be a reduced heat transport towards the north, because again, like the density difference in the ocean are important there. However, the Gulf Stream is not going to stop as long as we have wind and a rotating Earth. So there's good news.
That is good news.
I should mention that it's also really hard to measure these things, especially the timescales can be very long. There's different types of variability in our Earth climate that happens on decades. So there are big efforts in trying to measure the AMOC at different locations. But it is really hard to say precisely that the AMOC is slowing down or the Gulf Stream is slowing down, and particularly tying this to climate change. So we have a lot of work to do still.
Yeah, one thing, if I may add, is that we see a very clear indication of the oceans warming. And there was a study by one of our colleagues at WHOI that shows that the Gulf Stream itself is warmer. And over the course of the last 20 years, it's moved a little closer to shore. So if you try to, but as Svenja just said, there's so much variability in the ocean that it's one of the reasons we need long-term records to try to sift apart, like what's the natural variability and what's the variability that's coming or trend due to climate change.
Yeah, so we really need time series, observations that are longer than 20, 30 years to be able to pick apart these driving mechanisms.
Ken, let's take one more question.
Sure. I'm looking at the questions on Zoom, but some of my colleagues are watching on social media, and we have one from Facebook. Christina asks, can we go back in time to tell what the currents were doing before human observations?
That's a great question. Amala, I see you nodding. Do you want to take that one?
Okay, it's not my field, but I can say that we have some idea from what we call paleoclimate. So paleoclimate is climate of the past. One way we can reconstruct the climate of the past is by taking cores in the ocean. So you drill into the sediments or the ocean bottom and you pull out a core. And the core is in layers, and each layer is recording some history of the past. And so you can now analyze these layers in the core, and you can go back for a very, very long time, hundreds of thousands of years, millions of years actually, and you can look at past climate, and you can look at the isotopic ratios of different things in the core, for example, calcium-magnesium ratios and things like that. And looking at the isotopic ratios, we know that the fractionation of isotopes changed in warmer climates or colder climates. So you can kind of reconstruct a kind of average picture. It's hard to tell exactly the currents.
Mm-hmm. Mm-hmm.
I can add to that. So for example, cores we can also get from ice sheets. We just spoke about the Antarctic ice sheet. So it's similar to what Amala said. We can get these ice sheet cores and really look at the different layers and the compositions there. And then we can also use things like corals to reconstruct past ocean conditions, because they grow. So similar to tree rings, they grow depending on their physical conditions. If it's warmer, they might grow faster. If it's colder, they don't grow as fast. So we call them kind of paleoproxies. And I also have a colleague, for example, that works with clam shells off the coast here of the Northeast US. And these quahogs, their shells also grow incrementally like the tree rings, and they grow actually up to 500 years old. So they can really analyze again these different layers and get an idea about past conditions.
That's fascinating. So we've now talked about how currents can affect and be affected by global climate. I want to switch gears and talk about why currents and other types of movements of ocean water matter to marine ecosystems and to life in the ocean. Amala, why don't you start us off?
Yeah, so life in the ocean, just like plants on Earth, on land, are the primary food source for all other life forms on Earth. Plants in the ocean are the primary source of food for everything. And the plants in the ocean are microscopic, and they are cells, which we call phytoplankton. And these phytoplankton cells are drifting with the ocean currents. And what you're seeing here in this animation is a model that has simulated different kinds of phytoplankton in the ocean. The different colors are different kinds of phytoplankton. And so you get big cells of phytoplankton where there's lots of nutrients. You get smaller cells where there's less nutrients. And phytoplankton need nutrients, which is nitrate and phosphate, and they need light. So they grow close to the surface where they can receive sunlight. Sunlight then quickly gets attenuated with depth, because water doesn't let light pass more than 100 meters. It's completely dark in the ocean. And they need nutrients which are available in the deep, but these currents have to, through these instabilities or mixing, they have to bring these nutrients up to the surface and transport these nutrients around. And then the currents also transport the phytoplankton and the carbon around. And this organic carbon, a fraction of it that's produced by the phytoplankton gets sequestered at depth. So that's the carbon pump, or the biological carbon pump, that then sequesters this carbon and helps to keep our concentration of atmospheric carbon dioxide in check. So about 25% of all the fossil fuel emissions that we have put into the atmosphere have actually been taken up by the oceans, and it's partly because of the phytoplankton and partly because of the circulation of the oceans.
Okay, so the phytoplankton at the surface are taking up carbon dioxide that originated in the atmosphere, and then when they die, they're sinking all the way to the bottom. Some portion of them, right, is sinking to the bottom of the ocean, and then they're kind of trapped there, right?
That's right. So they sink to all different depths. And if they get very deep, then it's very hard for that carbon to come back up to the surface. And some of them just get recycled, but some of them end up, or they may end up in the guts of other animals like zooplankton. So it's the primary food source for other animals. So if other animals eat them and then produce fecal pellets, and those fecal pellets sink, then that's a sink of carbon to the deep ocean. So that's a good thing for right now for us.
Yes. Here at WHOI, we're in New England on the east coast of the US. Svenja, I'm wondering about the Gulf Stream, since that runs closest to us, and how it affects conditions out at the edge of our continental shelf.
Yeah, it definitely has a big influence on our coastal ocean here. So I mainly think about the physical properties of the ocean. And as you can see here in the image again, this is like a sea surface temperature image. With the white lines, they show the currents moving. So the Gulf Stream transport, as I said earlier, transports this warm, salty water northward. And this is a really interesting system because right along the coast, these purple bluish colors, this is actually different water that's originating from the polar regions, from the Labrador Sea, that's very fresh and cold, and that's flowing southward over our in our coastal region. So it's really this interplay of these and the relative contributions of those two water masses that kind of set our properties in our coastal ocean. And as we all know, the ecosystems, they strongly depend or respond to temperature changes. So we can have a change in the ratio of those two different water sources that can, for example, drive a warming. So what we have seen is roughly since 2010, our coastal ocean has been warming at a strong rate and accelerated rate. And there's research that indicates that since then, there was kind of this shift to a stronger influence of these warm Gulf Stream waters. I think Amala mentioned earlier that there's research from our colleague that this current moved a little bit northward, and it kind of limited the influence of this cold water coming south. And from what we hear from fishermen, that this warming really had impacts on the species compositions and the migration of species. So that's something that we're actively studying.
So that what's shown in red there, the Gulf Stream, right, is the warmer water, and that's actually coming closer to the coast, our coast
Right,
here, yeah. And influencing that darker blue and purple water to be warmer than it would normally be.
And in particular on long scales. I mean, we have variability on different scales. We call these wiggles, meanders. So there might be times of the year where the Gulf Stream comes closer to the coast anyway. But if we think about like decades in the mean sense, we can have a shift of this larger current northward. But there's always a constant, as we've heard throughout this evening, the ocean's constant in motion. There's these eddies, these swirling motions. So there's constantly exchange between those different waters.
Yeah, so let's talk more about what's going on where these sort of different waters meet. Gordon, what else is going on at the edge of the continental shelf, and how does the combination of what the Gulf Stream is doing, moving closer to shore, and other processes affect productivity and fisheries?
That's a great question, actually. That's a question I've been spent like last 10 or 15 years of my in the last at WHOI to work on. So that's the we call the shelf break. So if you look at the Google Earth, this one, you can see the continental shelf. It's relatively shallow. It's about 500 feet. And then at like 200 miles to the south or to the southeast of the coast, suddenly the seafloor drops down to thousands of feet. So that's a place where we call it shelf break. And that's also the place where the cold and relative fresh water from the subarctic region from the north that Svenja just described that came to meet with the warm water from the south. So that's a place where the cold water meet with the warm water. That's also the front Amala mentioned earlier. That's where the water property changed dramatically. So right at this shelf break and also this frontal location, we have this upwelling flow that I mentioned earlier. So they have this vertical flow that bring the deep water to the surface layer. So the deep water has high content of nutrients, and the surface layer relatively low. In the summertime, basically completely the nutrients being used out. So this upwelling flow, as you can see from this particular diagram, actually bring the nutrients to the surface layer where the phytoplankton can grow and has really high concentration of chlorophyll, which we can see from satellite, right? So, and also when we go out there, we make measurements and to look at the concentration of the chlorophyll or the phytoplankton, see there are a lot of them there. And because of the high concentration or high abundance of phytoplankton, there are more abundance of zooplankton, high abundance of zooplankton as well. So they eat phytoplankton. And then they attract fish. And all these fish come to this region, and the fish, they attract larger fish and the mammals, the whales, the dolphins, and also seabird. So several years ago, I went there several times on big vessels, and once we got there at the shelf break, you see all these seabirds flying around. You see all these mammals, whales there. And another thing you see, it's a lot of fishing gear. Right, so that's also because of the abundance of fish, all the fishermen go there as well to fish. And so there are a lot of commercial or recreational fishing activities going on right at the shelf break. So that's a place where the physics directly affect the biology in the ocean.
So lots and lots of activity going on at the shelf break, both by us and by animals in the water. All right, I think we have time for maybe one or two more audience questions. Ken.
Okay, sorry, stepping back to the previous section, a couple of people have asked whether currents can affect currents and typhoons, or I'm sorry, hurricanes and typhoons.
Maybe I can say a little bit about that. Yeah, so certainly. So one particular, I guess one way I'm aware of that is the Gulf Stream. Right, so they say in the Gulf of Mexico, sometimes you have the Gulf Stream that pinch off generate the eddy. I mentioned, so it's called, actually has a particular name called loop current. So within that loop current, and the water is very warm because it comes from the tropics, and sometimes has loop current, sometimes don't. Right, so that direct affect the temperature in that part of the ocean. And then if you have a hurricane passing by that region, and if there happen to be a loop current or Gulf Stream underneath the hurricane, so the energy of the hurricane, a lot of it came from the ocean, the surface part of the ocean, that heat released into the atmosphere, and then cause all this atmospheric circulation that drives the hurricane. So whether there's loop current or whether there's the hurricane just passed by the Gulf Stream or the loop current, that has a big impact on the intensity and also the trajectory of the hurricane.
So that warm surface water is basically fueling. It's like fuel to the hurricane.
Exactly. Yeah.
All right.
Yeah, well, typically what happens if the hurricane passes and you have just a thin layer of warm water, you typically have colder water beneath. So the strong energy of the hurricane will stir the water up and bring the cold water to the surface, so it will cool down and kind of not fuel the hurricane anymore. But if you have this big blob of really warm water that reaches into depth, you kind of don't have this mixing of the cold water, and you just keep fueling the hurricane and allow it to be strong.
Yeah, so that's why we're expecting to see more extreme weather events as our climate changes. Ken, let's take one more.
Okay, Gordon, you mentioned upwelling and its effect on driving productivity, but Carol asks if migrating animals and fish in particular, do they make use of the currents and actually ride the current? I'm thinking of the scene in Nemo.
You can see I can't wait to answer that question. That's a topic that I'm actively working on, and so again, the Gulf Stream or the the eddy came off the Gulf Stream. Also has a name called the warm core rings between the Gulf Stream and the coast of the northeast coast of the United States. So we know that from our recent measurements, we know that directly affect the migration of the we call mesopelagic fish. So there are fish living 2,000 feet deep. They migrate to the surface in the nighttime to feed, and then the daytime they hide. Some migrate down to hide, but they like to live in certain probably we're not 100% sure, but that's our hypothesis at this point, is that they like to live in certain temperature in the water with certain temperature. So when you have this warm eddy, right, that's a big blob of warm water. So some species just like stay in that warm blob of water. And the warm water moving, the eddy moving affect their habitat. So they affect their vertical migration. So when they migrate to the surface, they migrate down. If the water is gone, then they better move. So how deep they can migrate down, that's affected by that as well. So that's one of the mesopelagic fish. But then we also know that from our colleagues' recent work, is that sharks actually, they target those warm eddies as well, because they're more mesopelagic fish at the deep layer of these warm eddies. So when the sharks dive down to 1,500 feet, and they are more mesopelagic, more food there for them. So that's again a hypothesis. We're actively working on that.
All right, we're running out of time, but before we wrap up for tonight, I'd like to ask each of you one more thing, which is to tell us very briefly about a project you're working on right now and what you hope to learn from it. Let's hear from Gordon, and then Svenja, and then Amala.
Oh, so thank you. For me, so one of the things that I'm very excited at this point is also related to what we call the biophysical interaction. So how circulation or currents or temperature affect biology. So this particular application is a direction I'm actually working on is the coral reef hydrodynamics. So earlier we talked about all these large scale ocean currents, but there are also currents in this relative small scale, right? Hundreds of feet, or even tens of feet. Those affect the individuals living on the coral reefs. And so the condition over the coral reefs actually changes dramatically due to wind, due to tides, or due to the complicated topography. So here is an animation I made from a computer model we run for Zhang, which is an island in the US Virgin Islands in the Caribbean. And you can see the color here is the temperature of the sea surface, the 5 meters below surface. And then the arrows indicate the currents. You can see this is a relative small area. The entire extent of the island is about 10 kilometers, about 10 kilometers, about 6 miles or so. But you can see the temperature or the flow change dramatically from one side of the island to another, and also even from one bay to the next bay, or even sometimes if you look in one particular bay, it changes from one side of the bay to another side of the bay. So that means corals live in those areas, they experience very different physical environments. So that affects their growth, affect their health, and also affect their how their larvae, their baby is being transported. Right. So I'm working with biologists and chemists as well to look at how the hydrodynamics, the small scale hydrodynamics affect coral health, and how some of you might have heard from the news that corals around the world are dying because of either rising water temperature or because the disease. So we're trying to help them, trying to conserve them, protect them, or restore them. But then this kind of fine scale hydrodynamics, knowing them will help us to improve those efforts.
That's great. Svenja.
Yeah, I'm really excited about a project that we just started earlier this year, where we partner with the Cape Cod Commercial Fishermen's Alliance to equip, and so they're based here on Cape Cod in Chatham, and we're partnering with them to equip local fishermen with oceanographic instruments. And so this is really work that has been pioneered by Glenn Gawokowicz, my colleague, which you can see here on the right. And the fishermen get these instruments here on the left in this steel frame that they take on board, and when they go out fishing, they can actually take profiles. So they lower those instruments in the water, and we get profiles of temperature and salinity in those regions, and they can see the data live on an iPad once they bring the instruments up. And with that, we obviously hope to collect data in regions where we typically don't get to, or where we don't have the funding to get regular measurements in. But we also hope to foster exchange with the fishermen, and Glenn has been doing this over the past decade really successfully, to get in exchange with the fishermen, feed off their experience. They've been out there at sea for decades and know often much more about it than we do, and really tying in those changes that we see in the physical properties in the recent years with changes in fisheries, and just help each other out. Kind of, we can hopefully explain what's been driving these changes and what we might expect in the future, but as I said, also learn to make those connections to fisheries. So I'm very excited to see where this takes us.
Yeah, that photo is actually from an article I wrote about Glenn's partnership with fishermen probably 7 years ago or something along those lines. So I'm glad to hear the project is continuing. It's a great collaboration. Amala.
Yeah, so I'm very excited about a project that we just started with collaborators at the University of Ghana in West Africa. And I started to realize that about 40% of our oceans are warm or tropical oceans. By warm, I mean above 27, 28 degrees Celsius at the surface. And oceanography is an international science, but most of the resources for ocean science lie with the global north. So even though the oceans affect all lives across the globe, it's really most countries have not even started or begun their journey in studying their oceans. And this is a photograph that I took from a recent visit to Ghana. And you can see that the people of Ghana, the fishermen, the local fishermen, are really engaged with the ocean, and they're going out on these canoes and fishing. But there's very little data, very little observations, very little done in terms of modeling, because there's very little data in these coastal oceans. And we are starting a project with them. Piracy has kept away international research vessels for a long time, but finally we have a partner. The Schmidt Ocean Institute is bringing their research vessel into West African waters, and we are very excited to be making some of the first measurements in many decades in that region.
Very exciting. Unfortunately, that is all we have time for tonight. I want to say a big thank you to Amala Mahadevan, Svenja Ryan, and Gordon Zhang for joining us tonight to talk about our restless seas and their connections with ocean life, weather, and climate. Thank you, everybody.
Thank you. It was a pleasure. Thank you.
Thank you also to my WHOI colleagues who've been working very hard behind the scenes to make this event possible, and to everyone who joined us on Zoom, Facebook, and YouTube. Thank you. Tonight's event was the 5th episode of our 6th season of WHOI's Ocean Encounters events. Our next event will be on Wednesday, October 23rd. It's our season finale. And once again, we're going to be talking about paths to careers in ocean research, this time in geology and geophysics. Please watch our website, whoi.edu, for more details about that. In the meantime, you might want to take a look at the very cool merchandise on WHOI's online store, shop.whoi.edu. You get a 10% event discount for joining us tonight. Just type in the discount code CURRENTS. If you enjoyed tonight's Ocean Encounters program, you can be part of WHOI's solution-based approach to ocean science. If you're already a WHOI member, thank you very much. As you know, a benefit of WHOI membership is receiving our award-winning Oceanus member magazine. The upcoming issue, Ocean in Motion, is all about currents and will be in your mailbox very soon. If you're not yet a WHOI member, please consider joining so you'll never miss an issue. You'll get other great benefits too, and you'll be providing crucial support for our outreach and our science. Memberships start at just $40 a year. The average gift is $120, but any amount helps. On behalf of Woods Hole Oceanographic Institution, thank you and good night.
Out where the seas are the deepest and the mysteries the greatest lies our future. The ocean is our last unexplored, ungoverned frontier. The life support system for our planet, inextricably linked to our climate and weather, and to the lives and livelihoods of countless people around the globe. But even against the ocean's vastness, humankind can be a formidable force. What happens next demands action that is rooted in scientific understanding and unvarnished truth, because our world stands at a fork in the road. In one direction, we watch the ocean being catastrophically altered beyond its ability to sustain us. In the other, understanding outraces exploitation, and we help steward and protect this most precious shared resource. What will be the legacy of the 21st century? Together, we can unleash the world's most creative minds, passionately dedicated to ocean science, engineering, education, and policy. Together, we can provide the expertise needed to know what works and a trusted voice to present the facts as we uncover them. Together, we can shape the future. We can inform governments, businesses, and conservationists. We can generate new knowledge in service of society. We can be the catalyst for change. It is more than our responsibility. It is the defining moment of our generation. We are explorers, students, and stewards of the ocean, and this is our time.